Hello and welcome back. This is lecture slideshow 8 for week 8. Hello and welcome back. This is the lecture slideshow for week 8 of the Philosophy of Science course. For these slides, read handout 3 in Okasha chapter 2 and explore the links to additional content within Canvas module 3. For week 8, our topic question is, how does scientific reasoning work? This is also going to be the main question for week 9. This lecture is part 1 of 2, which will be continued in week 9. So what's the difference between science and non-science? Answer: testables. To understand this, we have to focus on science as a process of applied logic and controlled observation. A brief history gives us background into how modern science. To understand this, we have to focus on science as a process of applied logic and controlled observation. A brief history gives us background into how modern science operates. Brief review. What do we do for justification in science? The short answer is that we accept no hypothesis, description, or explanation without a good argument. That is, one which is logical in form and is grounded in acceptable, relevant, testable evidence. So what is science? This lecture will cover 1, 2, and 3 on this slide. So let's begin by discussing what I'll call deductivism. This is an arbitrary name. The point is, it's about the early logical beginnings of scientific thinking. Roughly, what I call deductivism is science is theoretical, truth-seeking knowledge deduced from what is demonstrable or axiomatic. We'll call the beginning of this, say, 300 years before the Christian era, up through the 1200s. New truths may be derived from prior truths. From general truths, we demonstrate what must be true of particulars. Unlike practical sciences, for example, politics or ethics, or the productive sciences, which are concerned with making arts and crafts, the theoretical sciences such as metaphysics, what exists, and epistemology, what can we know, seek truth. Here we're going to follow Aristotle. Science is the knowledge of things and their causes. We suppose ourselves to process unqualified scientific knowledge of a thing when we think that we know the cause upon which the fact depends. What I now assert is that at all events, we do know by demonstration. By demonstration, I mean a syllogism productive of scientific knowledge. The premises of demonstrated knowledge must be true, primary, immediate, better known than and prior to the conclusion. This is from Aristotle's Posterior Analytics. So in Aristotle's view, science explains by describing the causes of facts. If you want to answer the question, why does this event happen, or why is this object as it is, then one must state causes or aetia, which explain it. Aristotle had this notion of 4 causes for any why question. There's the material cause. For instance, looking here at the statue of David by Michelangelo, the material cause is that out of which a thing comes to be, the stuff of which it's made. In this case, it's marble. The efficient cause, this is going to be the primary source of material change. So it's the sculptor or the process of carving which realizes David in the material substance. The formal cause, this is its essence or the concept exemplified. It's the concept intended by the sculptor. For example, a statue of a youth, say David. And then there's the final cause. This is the goal or the purpose or ultimate end. For example, youthful human beauty being depicted by the sculptor. Formal causes and final causes are only the case for artificial or human-made objects, not natural things. They don't need formal or final causes. Material and efficient causes are sufficient to explain their appearance, behavior, etc. Aristotle thinks some knowledge cannot be proved, but scientific knowledge must be. Some knowledge is not demonstrative because knowing some of the premises of any argument are independent of demonstration. For example, axioms or self-evident truths. We just presume these. We can't prove these. I'll give you some examples later. Since we must know the prior premises from which the demonstration is drawn, and since the regress must end in self-evident truths, those truths must be indemonstrable. Some principles or axioms from which we derive conclusions. Here are three. The law of non-contradiction, sometimes also called the law of contradiction. This is the idea that contradictory propositions cannot both be true. For example, A is B and A is not B are mutually exclusive. They contradict each other. I mentioned this sort of contradiction when I discussed the notion of truth. There's what's called the law of excluded middle. This is the idea that for any proposition, either the proposition is true or its negation is true. You can't have both. For example, either Socrates is mortal or Socrates is not mortal. This entire statement, because of that or, is automatically true in virtue of its form alone. It covers all the possibilities. Third example, the indiscernibility of identicals. For any x and any y, where x and y are names, if x is identical to y, that is, if they name one and the same thing, then x and y have all the same properties. For example, Bruce Wayne is Batman. Different names, same subject. Water is H2O. A little more from Aristotle here. Syllogisms, or deductive arguments, are the subjects of logic. A deduction, syllogismos, is speech, logos, in which certain things having been supposed, something different from what is supposed results of necessity because of their being so. Each of the things supposed is an assumption or premise, protasis, of the argument. And what results of necessity is the conclusion, sumper asma. This is from Aristotle's Prior Analytics, Book 1, Parts 1 and 2. So to say that a conclusion results of necessity from premises, follows necessarily from premises, corresponds to the modern logic idea of a logical consequence. Conclusion C, where C represents our proposition, which is our conclusion. Conclusion C results of necessity from premises A and B if it would be impossible for C to be false when A and B are true. This is the definition of valid argument, one whose form guarantees the truth of the conclusion only if all of the premises are true. Deductions are one of two kinds of argument. We'll talk also about induction, epagoge. Induction is the reasoning process that moves from particulars to their generalizations. It is the basis of knowledge of the indemonstrable first principles of sciences for Aristotle. I return to this later. Here are a couple of syllogisms. Notice that the conclusions of each are different, although the assumptions of all of these are about the planets and in particular their motions. Take a look at the first argument, 1 through 3. All planets move on ellipses, with the sun at one focus. Pluto is a planet. Therefore, Pluto moves on an ellipse with the sun at one focus. What you need to see here is that if 1 and 2 are true, and either 1 or 2 might be false, but if they are true, the conclusion that Pluto moves on an ellipse also, with the sun at one focus, can't be false. Now, the argument would fail, of course, if either of the assumptions is false. The pattern would guarantee the truth of the conclusion only if all of the assumptions are true, and assumption 2, for instance, might be false. By the way, assumption 1 might also be false just in case there are planets that don't move on ellipses. Look at argument 4 through 6. Mars moves on an ellipse with the sun at one focus. Also, Mercury, Venus, Jupiter, Saturn are planets moving on ellipses too. Therefore, probably all planets move on ellipses with the sun at one focus. What you need to see here with this argument is that the conclusion doesn't necessarily follow. At best, it probably follows to the extent that you've got examples of planets in Claim 5, Mercury, Venus, Jupiter, Saturn, that move on ellipses. Those planets plus Mars move on ellipses. It gives you a pretty good reason to think probably all the planets, the thing about planets is that they move on ellipses. The second argument, 4 through 6, that's going to be an inductive argument because you don't get the guarantee that the conclusion is true, even if the assumptions are true. The first argument, 1 through 3, is going to be the deductive argument. It's valid in form. Question, of course, is whether it's any good. It could be bad if an assumption is false. In fact, any argument is bad if it contains one false or dubious assumption, regardless of the logic. But that's another way an argument can fail if its logic is bad. I'll say more about that later. This is what I mean by an ellipse on this diagram here. Take a look. This is how the planets move around the sun. So this is Aristotle's method. Derive necessary consequences from axioms, hypotheses, and alleged facts using valid logical syllogisms. Justified belief always requires arguments. A syllogism is an ancient word for deductive argument. Here are 3 examples. Here's an example of a categorical syllogism. It's based on an all or nothing sort of statement. All planets orbit the sun. Earth is a planet. Therefore, Earth orbits the sun. There is no way, if Earth is a planet, it cannot be orbiting the sun. If it's true all planets orbit the sun, the conclusion Earth orbits the sun necessarily follows of necessity. Okay, disjunctive syllogism. What's that? A disjunction is an either-or statement. And so a syllogism, which features a disjunction, reasons like this example. Eyes, complex eyes like those of humans, mammals, formed by accident, or they were made by a designer deity, namely God. Well, if you can show this, if you can show eyes did not form by accident, then you have proven eyes were made by a designer deity, namely God. So see, the disjunction, which is the first claim, gives you 2 possibilities, and if they are exclusive, ruling out one means the one remaining must be true. Hypothetical syllogism, it's called this because it uses hypothetical claims, if-then claims, to generate another claim, namely another hypothetical claim. Consider the reasoning here. If that is a spider, then it's venomous. Another way of saying this is that all spiders are venomous. If it's venomous, then its bite is lethal. So we may conclude necessarily that if that's a spider, then its bite is lethal. This form is valid because it guarantees the truth of the conclusion. If you like, the conclusion is actually contained in the premises, in the assumptions. Now, the argument could fail and be valid. It could be bad, even if it's valid, if one or more of the assumptions is false. We don't judge an argument based on the truth or falsity of its conclusion. We judge it based on the evidence, the truth or falsity of the assumptions. What makes an argument valid? Answer: its logical form, its pattern of reasoning, not its content, that is, its individual assumptions. There are 3 ways to describe validity. They all mean the same thing. They imply the same thing. It's 3 ways to think about it. An argument is valid if it has the following property. If all the premises are true, the conclusion can't be false. That is, it's logically impossible for the premises to be true and the conclusion false. The truth of the premises guarantees the truth of the conclusion. You'll notice that inductive arguments can't do this. So here comes my brief introduction to logic in science, or how to use logic to justify claims, scientific or otherwise. Here is the traditional square of opposition. I gave you a very brief look at this in the first lecture. I want to give you some more details so you understand this relation between these propositions. That is, the sorts of immediate inferences deductions, which are derivable from the necessary relations between these claims, these four types of propositions. Take some time with this. Look at these slides and notice the relations between them. For instance, every S is P. If true, you'll notice is the opposite of some S is not P. We call those contradictory claims. Same goes for the claim no S is P and some S is P. If you say no pit bulls are vicious and someone says but some pit bulls are vicious, then you've got a contradiction going on. When you've got a contradiction, it means that one is correct and the other is not correct. That is, when one is true, the other's got to be false. They both can't be true. They both can't be false. I'll give you some more examples. I want to define some of these logical terms. I will never ask you on a test whether claims are consistent, contradictory, contrary, or subcontrary. That's for a further logic course, which I recommend you take. But for the sake of these presentations, it's good to be familiar with these terms. A set of propositions, and again, a proposition is the meaning of a declarative sentence. A set of propositions is consistent if and only if that set does not contain any contradictions. So a person tells a consistent story so long as it doesn't contain any contradictions. Now, two propositions are contradictory if and only if one is the denial or negation of the other. That is, they cannot both be true at the same time, and they cannot both be false. One's true, the other's false. Which one? Who knows? The issue is you've got a contradiction. Contrary claims. Two propositions are contrary if and only if both cannot be true, though both could be false. Two people could be disagreeing, and they're both wrong. For example, all pit bulls are vicious is contrary to the claim no pit bulls are vicious. They're not contradictories, they are contrary. Both could be wrong if some are vicious and some are not. Two propositions are said to be subcontrary, and nobody uses these words except for logic professors. Two propositions are subcontrary if and only if both cannot be false, although both can be true. For instance, some pit bulls are vicious is the subcontrary of some pit bulls are not vicious. Both can be true, but both cannot be false. And when I say P implies Q, or that one claim implies another, P implies Q if and only if whenever P is true, Q also is true. P doesn't make Q true. What we're saying here is there's this necessary relation between P and Q, namely that whenever P is true, so is Q. To say that when P is true, so is Q, or to say that P implies Q is not equivalent to saying Q implies P. That's a separate issue. Notice the claim P implies Q is about P. P is your subject. Q is your predicate, what you're saying about the P's. Examples, again, written out for you here, consistent claims. This pit bull is vicious, and that pit bull is not vicious. Both can be true at the same time. They're compatible claims. Consistent is compatible. Contradictory. Here we go. All pit bulls are vicious, and some pit bulls are not vicious. Yeah, those two claims cannot be true at the same time. One claim is true if and only if its negation is false. So if it's true that all pit bulls are vicious, then it's not true some are not. Or if it's true that some are not vicious, if it's true that some pit bulls are not vicious, it isn't true that all pit bulls are vicious because some are not. Contraries. All pit bulls are vicious, and no pit bulls are vicious. Both claims can be false. But both cannot be true. Subcontraries. Some pit bulls are vicious and some pit bulls are not vicious. Both claims can be true. Implication. Implication is a special logical relation. It is not the same thing as saying anything about causation or causal relations or correlations. Separate issue. This is logic. If all pit bulls are vicious, I don't know whether they are, but if they are, this would imply that some pit bulls are vicious, right? All implies some. All lives matter implies some lives matter. Or, if no pit bulls are vicious, then some pit bulls are not vicious. The claim no pit bulls are vicious implies that some pit bulls are not vicious. Some is a subset of, some are not is a subset of none. The antecedent condition implies the consequent, where the antecedent is the first part. All pit bulls are vicious. The consequent is the second part. Some pit bulls are vicious. We're expressing in an implication this necessary relation between the antecedent and the consequent, where the antecedent implies or means that the consequent follows. Summarizing here, a lot of logic here. Again, I just want you to be familiar with these terms. Never going to ask you whether a claim implies another claim. That's what we do in logic, although it's a very powerful tool, and that's the point. In science, we need to use it. To say that P implies Q says that whenever P is true, Q is also true. In the claim P implies Q, P is the antecedent condition and Q is the consequent. P implies Q, where P is a proposition and Q is some other proposition. P implies Q is equivalent to saying if P, then Q, which is the same thing as saying all P are Q, which is the same thing as saying the only P are Q. Suppose I say all lives are lives that matter. Then I'm saying if a life matters, if all lives matter, then any life matters. So an implication statement is the same thing as a conditional statement, which is the same thing as a hypothetical statement. So you can interchange hypothetical and conditional and implication. Same idea. Logical implications are false, always, whenever the consequent is false. That is, if the first part's true, if the antecedent condition is true, and the consequent is false, this is possible. Then the claim is altogether false. In fact, this is how we're going to test implications. If someone says, if P then Q, and you show an instance of, hey, I have a P, but I don't have a Q, you show the claim P implies Q is false. It isn't necessarily true that if someone says P implies Q, or P means Q, that the implication is true. If I say P implies Q, you realize that just because P is true doesn't mean Q is true, would show that the alleged implication is false. Okay, here's an example of implication and how to test and ultimately reject an implication. I hear a blue jay outside my office as I'm recording this. So how about this? If I hear a blue jay squawking, then there is a blue jay squawking outside of my office right now. Now, it isn't automatically true that just because I hear a blue jay, that there is a blue jay squawking. For all I know, I open the door, I look. It's a person playing a recording. It's someone doing an imitation. I'm hallucinating. Those are three alternate explanations. So suppose, again, my implication that I'm testing, the hypothesis that I'm testing is that if I hear squawking, then there's a blue jay outside my office squawking. That implication would be false if I heard the squawking and it was someone imitating a blue jay outside my office. You see it? So just because I hear squawking doesn't mean there's actually a bird squawking. So that's how implication works. It says that on the condition that you hear the squawking, there's going to be a bird outside your office. For real, doing the squawking. So implications aren't automatically true, although the way people state them sounds like they're going to be true. We let people presume them when we should be testing them. If A, then B, only says that when A is true, so is B, but the implication, if A, then B, would be false if you had an A but not a B. If you had a bird squawking sound, you hear birds squawking, and yet outside the office there's no squawking. All right, so we need to make some additions to Aristotelian logic. This is purely an historical point from the 1930s to now. Aristotelian logic evolved into something called natural deduction. A natural deduction is a logical proof procedure by which the conclusion of an argument is derived from the premises by using rules of inference, step by step. Rules of inference justify the steps of a proof. A proof, also called a deduction or derivation, is a sequence of steps in which each step is either a premise or follows from earlier steps in that sequence, according to the rules of inference, the rules for drawing conclusions. Notice the term proof here is not the ordinary language notion of proof. A proof isn't like showing something's true. A proof is a kind of demonstration in Aristotle's view. A proof is a showing. A proof is an argument. It could fail. Just because you've got a proof doesn't mean it's true, doesn't mean it succeeds. We call arguments good or bad, valid or invalid, strong or weak. We don't call arguments true or false. We call the assumptions true or false, or the conclusions true or false, given the justifications, the proof. Again, a justification is a justification of a step includes a rule of inference and the prior steps that were used to derive it. This procedure guarantees that each step follows validly from prior steps. A proof ends when the conclusion of the argument has been derived correctly. Now, you have to check it to make sure no one violated a rule of inference. A rule of inference here being something like categorical syllogism, hypothetical syllogism, modus ponens, modus tollens, etc. I mentioned those. You'll see those in some of the examples I have for you. Again, I will never ask you whether an argument is using modus tollens. However, modus tollens reasoning is going to be featured when we talk about falsifiability. Syllogistic logic is great. We need it. You've got to use it. However, it has limits. Here are some of the problems. Deduction doesn't really explain anything or generate new knowledge. Again, what we want in science is explanation, in addition to description. Reasoning by syllogism only reveals truth when you have truth to begin with. All planets orbit the sun. If true, fails to explain why Earth orbits the sun. It only establishes that Earth does. Number two, it's not true that you know something only if you can prove it. Aristotle agrees. Axioms can't be proven. We just assume them. For example, here's an axiom. Again, an axiom is a self-evident truth, one for which we cannot give proof. We just presume. And it's not that easy. It's not just that we believe it based on faith. We believe it because we have never found, you would be famous if you could find an exception. For instance, recall from mathematics, when an equal amount is taken from equals, an equal amount results. This is how you get through algebra. Reasoning by syllogism is truth preserving, not truth generating. For that, we're going to go to induction. Number three, some knowledge can't be proven by deduction. There are basic beliefs that don't require demonstration, which nevertheless may function as foundations supporting other beliefs. You can't prove that you exist or that an external world exists. We presume these things. We can't prove that you ever perceive the world accurately, and yet we presume we do sometimes, even though we might not know when we do. And yet we know these things, right? We know that we exist. We think. We think we know. At least we must proceed as if we do. There are other non-deductive sources of knowledge. Moving on, the second trend is something I'm going to call classical empiricism, where classical empiricism is roughly all ideas derived from sensory impressions. Deductive reasoning is limited. Without observations and experiments, it is impossible to know reality thoroughly. So what we add to syllogistic logic is observations and experiments. I can think the idea of a horn and the idea of a horse together and get a unicorn. This doesn't prove they exist, but I can get the idea of a unicorn from my experience of horses, my experience of horns. Okay, I'll call this second trend in the history of science classical empiricism. Again, I use this term the way my philosophy of science teachers did. It's just a practical way to refer to the idea that without experience, it's impossible to know reality thoroughly. We can't just sit around and do logic. We have to observe the world. Here's Roger Bacon around the year 1268 in his work on experimental science. There are two modes of acquiring knowledge, namely by reasoning and experience. Reasoning draws a conclusion and makes us grant the conclusion, but does not make the conclusion certain, nor does it remove doubt, so that the mind rests calm in the intuition of truth, unless it finds this certitude by way of experience. Thus, many have arguments toward attainable facts, but because they have not experienced them, they overlook them and neither avoid a harmful nor follow a beneficial course. Even if a man that has never seen fire proves by good reasoning that fire burns and injures and destroys things, nevertheless the mind of one hearing his arguments would never be convinced, nor would he avoid fire until he puts his hand or some combustible thing into it in order to prove by experiment what the argument taught. But after the fact of combustion is experienced, the mind is satisfied and lies calm in the certainty of truth. Therefore, reasoning is not enough, but experience is. The scientist is first and foremost an observer. Here's David Hume in his Treatise on Human Nature in 1739. All of our ideas originally derive from impressions of the senses. A matter of fact can never be proved by reasoning a priori, prior to experience. It must be discovered or inferred from experience. Thus, all knowledge is a posteriori, after experience. Reason only contributes to the analysis of concept. We need reason. Reason tells us about the meanings and conceptual connections, but nothing about whether something is a fact or what causes an event. Without the checks and balances of observation and experiment, tradition, common sense, definitions, and deductive logic enable us to mislead and delude ourselves. The reality of unicorns or sea monsters cannot be demonstrated by reason alone, though we can imagine them. We can imagine, using logic, what they would look like. People believed in unicorns and their magical properties. Numerous works of art and literature refer to them. Sea monsters appear on many ancient and medieval maps. Now, classical empiricism has its problems, has its limits. And again, for each of these trends, I'm going to say we're adding to the idea of how science works, of how scientific reasoning operates, by incorporating new findings, new philosophical thoughts. Number one, the scientist is first and foremost an observer, but there are other sources of knowledge besides experience, logic, arithmetic, geometry, produce knowledge not based on sensory experience, which we cannot do without. We don't observe that a squared plus b squared equals c squared. Number two, knowledge also rests upon essential but non-empirically based principles not based on experience, observation. We can't draw a generalization from samples without assuming that properly chosen samples are representative of the whole population from which they are samples, which is at best only probable, never certain. We cannot make successful predictions about future events without presuming that nature is somewhat predictable or that the future resembles the past. David Hume will make much of this presumption shortly. The third trend, I'll call it inductivism. And I call it inductivism because what's happening is we're incorporating inductive reasoning, that other form of reasoning Aristotle referred to. Inductivism. Science is knowledge derived from experienced facts. It begins with particular observations and then makes generalizations or predictions. On this image here, we see logic of two forms. We see deduction, where from general principles, axioms, presumptions, we derive specific cases, specific instances, specific conclusions, where the conclusion is contained within the assumptions, the principles. Induction works the other way. That is, from specific cases, we draw a more general conclusion. And again, induction doesn't generate a conclusion which is necessarily true, only that's in general true. Generalizations aren't true always, everywhere, but they're useful. When I talked about the example of the planets, where we notice of several planets, each of them moves on an ellipse around the sun, and we draw the general conclusion that that's the thing about planets, they move in ellipses around the sun. It isn't necessarily true. For all we know, there might be a planet that doesn't move in an ellipse around the sun. Still, in general, we see the more examples we have of planets moving in ellipses, the more we think probably that's the thing about planets. What is justification in scientific reasoning? Again, scientific reasoning requires both logical argument and testable evidence. I'll say a lot more about testable evidence when we get to positivism. Faith-based or emotional reasoning does not. There are going to be these two kinds of logical reasoning now. We can put them together, deduction and induction. If an argument is deductively valid and all of its assumptions are true, then its conclusion is necessarily true. That's a very powerful logical relation between presumptions and conclusions. If an argument is inductively strong and all of its assumptions are true, then its conclusion is probably true. So we've got deduction and induction. Deductivists think that only deductive reasoning justifies knowledge. Most people disagree. This is an academic debate. Be careful. Don't confuse the form of an argument, the logical pattern, with its content, that is, its alleged facts and assumptions. An argument may have a truth-preserving, valid, or truth-generating, strong form, but dubious content. Such an argument cannot be a good justification for a belief or hypothesis. There are these two ways arguments can go wrong. They could either have bad form or bad content. You need to satisfy both. Review carefully these examples. What I'm doing in this slide is comparing, contrasting deduction and induction. 3 columns here. Valid, strong, weak. On the left, the first column, and only the first column, represents deductive reasoning. Here is a pattern of deductive reasoning. There are other patterns. This pattern is valid. Here's why. We presume that all A are B, and X is an A. Therefore, X is a B. That's an inescapable conclusion. If it's true, all A are B, and if it's true, X is one of those A's, then X is going to be a B. Concrete example. All actors are robots. Tom is an actor. Therefore, Tom is a robot. Now, yes, it's not true that all actors are robots, but do you see that if it were the case that all actors are robots and that Tom is an actor, that Tom would be a robot necessarily too, right? Again, a valid argument isn't necessarily a good argument. It's only good if its assumptions are all true. Valid doesn't mean good. It just means it's got this form that preserves the truth. What does that mean, to preserve the truth? Well, if the assumptions are true, then so too is the conclusion, on the condition that it's got a pattern, such as this one here. This is a case, say, of categorical syllogism. Let's look at the 2 columns on the right, strong and weak. These are forms of inductive reasoning. I'm going to leave it as an exercise to the viewer here to look at these more closely and figure out how the logic works here. A strong argument is one whose conclusion is probably true given the truth of the assumptions. And it's going to depend upon those assumptions. So the difference between a strong and a weak argument in this case is going to be the term most versus the term some. Example, most A are B, X is an A, therefore X is a B. Or almost all A are B, X is an A, therefore X is a B. Example, most actors are robots, Tom is an actor, therefore Tom is a robot. You can see, because we're saying most, not all, that the best it can be is that probably Tom is a robot. That's an inductive argument. And it becomes weaker to the extent that you have fewer examples. And in fact, if you just have one example of an actor that's a robot, you see that the argument is much weaker, in fact, bad. I'm going to call weak arguments bad, strong arguments good, valid arguments can be good so long as the assumptions are true. Here's an example of a nice weak argument. Some A are B, X is an A, therefore X is a B. Some actors are robots. Tom is an actor, therefore Tom is a robot. Yeah, some could be at least one or several. But that wouldn't license us thinking that Tom, being an actor, is also Tom is a robot. Again, contrasting the two here, in deductive logic, the conclusion follows with certainty from the premises, whereas with inductive logic, the conclusion follows not with certainty, but only with some probability. These are called risky inferences, but that's okay. We need these because we want to be able to talk about the future. We want to be able to make generalizations that aren't necessarily true, but very useful in guiding our behavior and judgments. Look at the inductive logic argument. Suppose it's true that 90% of humans are right-handed. John's a human. Therefore, we draw the conclusion that John is right-handed, probably. Or we could say, there's a 90% chance that John is right-handed. We are fully aware that maybe 10% of humans are not, and that John could be among them. But this I'm going to call a strong argument because of the 90%. It becomes weaker as that percentage decreases. I'm going to say if it's 51% or more, you can call it strong. It's better the larger the percentage of your sample observed. Below 50%, you're going to get a weak argument. It's a bad argument. Let it go. Again, inductivism is science, is knowledge derived from experience, facts, and probabilistic reasoning, where science describes, collects, and classifies sensory data. An inductive inference is one whose conclusion, while not following deductively from its premises, is in some way supported by, or rendered more likely, if the premises are true. Conclusions are only probable at best. That is, given that the premises are true, the likelihood that the conclusion is true is more than 50%, or should be, for you to consider that a justified, strong, inductive argument. Induction offers a rational way to generalize, predict, and test explanations without needing to provide any guarantee that our conclusions are necessarily true. Inductive reasoning allows us to go beyond what evidence conclusively implies. This permits us to generate a new knowledge, unlike deduction, which only can tell us what follows from what we already presume or presume to know. I want to give examples of 5 kinds of induction here. I'm never going to ask you to identify the kind of induction, but I want to show you how this works. Recall that an inductive argument is inductively strong, if and only if it is improbable that its conclusion is false, while its premises are true. Strength or weakness depends upon those assumptions. An argument is only as strong as its weakest assumption. You're familiar with these. I'm going to focus especially on statistical induction and causal induction, but let me mention the examples with which you are probably already aware. There are arguments by example. It's also called enumerative induction, where you count up all your cases and then draw a generalization. From all observed swans are white, we infer probably all swans are white. Again, we go from what we've observed to the larger set of all of the swans. Another conclusion, the next swan observed will not be black. Arguments by analogy or comparison support claims by comparing similar cases. For instance, monkey respiratory physiology is sufficiently like that of humans, so what is true of one respiratory system is probably true of the other. And this assumption is what supports the use of monkeys in research, say in air pollution research or in smoking research, because what we see is true of the monkeys, namely smoking increases the risks for particular lung cancers. We can extrapolate, we can say that's probably true of humans because we have the same respiratory tree. Statistical induction is used primarily for generalizations and predictions. You're already aware of statistical induction when you're reading these peer-reviewed studies in journals that I've had you look at in discussions. We'll also here talk about causal induction briefly, and then I'll come back to reasoning about causes and effects in another lecture. We use causal induction whenever we explain phenomena, explain what we observe. There's also something called eliminative induction or abduction, and this is what we use when we decide which theories to adopt, at least temporarily until better theories come along. Again, this comes up later. Be careful how you use and judge generalizations. A categorical generalization is not the same thing as a statistical generalization, because a categorical claim is not the same thing as a statistical one. For instance, here's an argument. Argument A. Suppose it's true that all ravens are black and that R is a raven. Therefore, R is black. Since R is a raven and all of the ravens are black, R is going to be a raven. R could denote any bird that is a raven. R could be the name of the bird. We get this conclusion from the categorical generalization, the generalization about the category, namely of ravens, namely all of them are black. Contrast that with argument B, which is inductive. This is statistical. Statistics. Statistics are descriptions of properties of samples of populations, and we use statistics to say something in general about the population from which the statistic or the sample was drawn. For instance, take the claim most ravens are black. All the ravens I've ever seen are black. R is a raven, therefore R is black. And again, this is really saying probably R is black because R is a raven and most of them are. But notice the guarantee's gone. We aren't able to say for sure with certainty that R is black just because R is a raven. Again, I'm presuming that claim 4 and claim 5 are true. At best, we can say probably R is black because R is a raven. Now listen, I'm telling you, there are ravens that are not black, but they're rare. So this argument's strong. You could go so far as to say 95% of ravens are black and conclude that new raven R is black. Reasons for rejecting a categorical generalization and its associated argument are not good reasons for rejecting a statistical generalization. All ravens are black would be shown false as soon as we had a non-black raven. However, the claim most ravens are black would not be shown false just because we have 1, 2, 3, 4, 5, 6, 7 non-black ravens. Any exception to claim 1, all ravens are black, devastates it, shows it's false. Exceptions to claim 4 weaken it, yes. You might lose the most as soon as you drop below, say, whatever your number is, 65, 70%. Argument A has valid form. Argument B has strong form. Argument A is deductive. Argument B is inductive. Neither is good if any of the assumptions is demonstrably false. Here are examples of argument forms, inductive argument forms in science, using generalizations and predictions. For statistical induction, I'm going to give you a more detailed example. I want you to take your time going through this. I'm just going to hit the highlights right now in this recorded lecture. It's a little too detailed to expand the lecture beyond your attention span. Number 1, the median annual earnings for Americans 25 and older who graduated from high school but did not attend college was $29,815. The median annual earnings for Americans 25 and older who graduated from college but did not complete any level of graduate school was $52,019, almost twice as much. Notice claims 1 and 2 are statistical, right? They're based on observing samples of Americans 25 and older and looking at their annual earnings. Conclusion, the median earnings for college graduates was $22,000 or 74.5%, greater than the median income for high school graduates. Is it saying it's true for each of them? No, it's saying for the population observed. Let's use statistical induction, those statistical generalizations plus the conclusion of that previous argument, and math. Mathematical deduction, arithmetic, that's the same thing. How do you make $1 million? Here's an argument. And this statistical inductive argument is going to yield a prediction. The prediction is you will earn over $1 million if these conditions obtain. The U.S. Stock Exchange trades stocks for about 2,800 companies. The S&P 500 index is a diverse composite of 500 stock listings from the New York Stock Exchange. The average annual rate of return since adopting 500 stocks into the index from 1957 through 2018 is about 7%. So on average, you earn about 7% a year. So if you invest $6,000 per year in the index, for example, in a mutual fund, for 40 years, you will earn over $1 million. I'm going to have to show you some details here, but that's the prediction, and it's based on those numbers and some assumptions. Here's a chart showing the average annual return for the S&P 500 for the past 50 or so years. This is where they get that 7% number. Look, there have been bad years. So in 2008, it was down over 38%. Here are my sources for average annual return for the S&P 500, and I'm also using a compound interest calculator. I think you should spend some time playing with one of these. Let me give you an example of how compounding interest, saving your money and compounding interest, can make you a millionaire in 40 years or less. I do this because I want to demonstrate the value of deduction, induction, and philosophy, making predictions based on statistics, not knowing necessarily you will be able to earn $1 million in 40 years, but trying to show you probably will, since most people who do this and get this 7% annual return. Here's a little chart showing you what compound interest is. If you're not already familiar with this, you should be. Look at this chart, Google it. Compound interest is your friend. So the presumption of this argument, I'm going to highlight it here to make it really clear. This is an inductive assumption. If a sample accurately represents the population from which it is drawn, and of course it might not, but if it does, then probably whatever is a property of that sample is also a property of the entire population. Now here's the math, here's the calculation. Use a compound interest calculator, 40-year horizon. Imagine you start with nothing, but every year you save $6,000. The average annual interest rate is 7%. That's based on the past 50, 60 years of data on average. Some years are high, some are low. That's the average. 40 years to grow. Every year, compound interest accumulates once. By the end of 40 years, if you can put away $6,000 a year, and that's it, you will be worth $1.2 million. So you see, if you put away more, you'll be worth more. By the way, it's a good idea to do now, and I'm telling you, when you're 19, 20 years old, you should start saving now. I don't know about the $6,000, but save at least 10%, 20% of your income. I know that sounds crazy. You're used to earning less, living on less, but once you start earning more, you should save more. If you wait until your 40s, you'll never get near that $1 million mark. I recommend you take at least one of these courses while in college. Here is what Sac State offers. I have a little argument here on another way to motivate you to save money in the way I've described by taking advantage of compound interest. I call it How Not to Lose a Small Fortune, and I'm going to refer you to that article. Here is the URL at the bottom of this slide. Okay, so I've described examples of induction by example, analogy, and using statistics. Let's move on to causal induction. Here's a claim with which you are familiar. Smoking causes fatal lung cancer. These are human lungs. The one on the left is one of a non-smoker. The one on the right is the one from a smoker. So there's a visual difference if you're actually able to do an autopsy and look. But what does it mean to say that smoking causes fatal lung cancer? There are some possible answers. Does it mean if you smoke, you're going to get cancer? Or does it mean if you get cancer, then you were a smoker? Or does it mean if you don't smoke, you don't get cancer? Does it mean all smokers get cancer? Does it mean only smokers get cancer? In fact, none of the above is the best way to interpret that claim, and yet lots of people interpret it that way. I think the best way to interpret this when someone says A causes B, or say smoking causes cancer, is to read it like this. Smoking is a cause of cancer. Smoking raises the risks of developing certain cancers. That's as good as it gets. There are no guarantees that smoking is going to give you cancer. You could get cancer without the smoking. I have a lot more to say about this when I get to causal reasoning. Right here, I just want to show you an example. Nobody who says smoking causes cancer or sex causes babies is saying that smoking necessarily causes cancer or always causes cancer. or that sex necessarily causes babies. The idea is that when the antecedent condition is satisfied, the smoking or the sex, then the consequent is more likely or more probable. Smoking increases the risk of cancer. Sex increases the risk of babies. Here's an argument about a cause and effect. Many smokers are afflicted by chronic bronchitis, asthma, emphysema, heart disease, mouth and lung cancer. Heavy smokers suffer these problems even more so than do light smokers. Furthermore, non-smokers living with smokers suffer these problems more than non-smokers who don't live with smokers. Obviously, smoking causes these problems. Conclusion is smoking causes these problems based on these observations, these statistics. What it presumes is something like the following, and every causal argument assumes this whether or not it says it. And such arguments stand or fall based on the strength of the correlation. We've talked about correlations. If there is a strong correlation between X and Y, where X and Y don't accidentally coincide, X and Y do not have a common cause, some other factor producing both of them, and Y does not cause X, it's not reversed, then probably X is a cause of Y, something which increases the likelihood of Y. Finally, let's discuss eliminative induction, okay? Eliminative induction, or abduction, supports claims by ruling out contrary claims. Given a finite list of theories, there's only so many theories we can entertain at one time, models, hypotheses, and presuming that only one is true, once you prove one is false, or you eliminate all but one of them, you may conclude that the remaining one is probably true. This is not a guarantee. This is similar to disjunctive syllogism, which I showed you in an earlier slide for this lecture, but it's not the same. Example from John Stuart Mill. If two people resemble one another, then either they share a common ancestor, a common cause, or one caused the other. Since one did not cause the other, they probably have a common ancestor. We can only ever say probably because perhaps cosmetic surgery happened and someone wanted to look like their celebrity fixation. Scientific reasoning then features both deduction and induction, used in concert. The point, whether an argument is inductive or deductive is not important, not here. Instead, what matters is whether the evidence presented in an argument necessarily or probably justifies believing the conclusion. We proportion belief in a conclusion based on the quality and quantity of evidence. Arguments are essential to justifications in science. Without evidence for a hypothesis, there is no justification. Briefly, I want to summarize something I mentioned before about form versus content. The way to prove an argument is bad in science or outside of science, using logic, and these two essential features, namely logical form and factual content. Either we show that its form is illogical in some way because it is either not truth-preserving, not deductively valid, or not truth-generating, inductively strong. An inductively weak argument does not satisfy the logic check or the form test. You could also show that its content, at least one of its assumptions, is incredible, dubious, just plain false. Good arguments, by comparison, are less vulnerable to these problems than are bad arguments. We call this check the fact check. I call it the reality check. So arguments have to be good in two ways. They have to have proper form, logical form, and they have to presume what is probably true or demonstrably true. Summarizing, what makes an argument good? A good argument must be either valid or strong in its logical form. This is necessary, but it's not sufficient. A good argument must also have all true or plausibly true assumptions. This is necessary, but not sufficient, not enough. Thus, an argument is good if and only if it is either valid or strong and it has all true or plausibly true assumptions. There it is. That's an argument for what makes an argument good. Be careful here. Any argument that is not good is bad. There's no in between. Let me show you an argument that is valid but not good. And it's going to be bad because even though it passes the logic check, it fails the fact check. 3 claims. All spiders have 10 legs. All 10-legged creatures have wings. Therefore, all spiders have wings. You should see from this is a case of hypothetical syllogism. Look it up. You should see from this that if you've got yourself a spider, then you've got something with 10 legs, according to this argument. And that if you've got something with 10 legs, then it's going to have wings. And so we should conclude, if you've got a spider, you've got something with wings. Now, on reflection, considering your experience, you should know that no spiders have 10 legs. But all you need is one spider without 10 legs, naturally, not plucked off. And you would see that claim 1 is false, in which case the argument would fail. Or, look at claim 2. All 10-legged creatures have wings. Well, you can name a 10-legged creature that doesn't have wings. In fact, you could probably name several. And you would demonstrate that claim is false. Crabs, shrimp, 10-legged creatures, no wings. So claim 2 is false. So not only is claim 1 false, so is claim 2. So is claim 2. All you need is one of these claims to be false. Argument fails. It's not good. Fails, the reality check passes the logic check. It's a bad argument because at least one of the assumptions is false, so even though its form is logically valid, it fails the reality check. Here I contrast the difference, finally, for you between deductive and inductive reasoning with respect to the planets. Be aware that induction is not deduction, and what I mean is that inductive reasoning never implies conclusions. Only deduction implies anything. So don't criticize every argument by saying that the conclusion doesn't necessarily follow. It makes no sense to say this, since the conclusion of an inductive argument is only, at best, probable. Always. Never necessary. Deductive arguments can't go beyond the scope of the premises. Can't go beyond what the premises assume or assert. Only induction can do this, but at the cost of losing that guarantee that the conclusion is true. These are features of each of these forms of reasoning, not problems. Use each only when you accept their limits. Scientific reasoning does proceed from particular observations to general theories. However, inductive reasoning is notoriously unreliable if we seek certainty. The result is that we give up on certainty, but still use inductive reasoning to discover and test theories. I'm going to say more about this in the next lecture. Inductive arguments project observed regularities onto unobserved cases, past, present, and future, based upon philosophically unjustifiable assumptions. This is going to be called Hume's problem of induction. The result? We can't prove alleged facts about unobservables, things we can't observe or measure. So we evade the problem by speaking probabilistically and say, at best, we can only disprove a hypothesis. So we don't prove, we disprove. Up next, logical positivism and beyond. This will be part 2 of this 2-part lecture. And we'll talk about the infamous problem of induction as David Hume described it. Read all of handout 3 now. Logic, Empiricism, Positivism, A Brief History. See also the shorter handouts in Canvas under assigned reading 3A, handout 3, 3A, B, C, and D. Read also the Ayer, Popper, Hempel, Hume excerpts available in Canvas Module 3. This is the end of the slideshow.